Hey guys, so today we're going to be talking about anodizing titanium. And if you don't know, anodizing titanium is essentially changing the color of the metal through an electrolytic process, through electrolysis. I'm going to have an experimental portion of this video and then a theoretical portion. First, I'll show the experiment itself, where we're going to anodize a little piece of titanium metal. And then I'm going to go more into detail on how the anodization itself works, and then on why it changes the color of the metal. Yeah, so that's going to be it, and I'll get right into it. So I just I stripped the oxide layer off of this titanium workpiece using first hydrofluoric acid, and then I neutralized that hydrofluoric acid using ammonium hydroxide, and then I currently have it submerged in water. So here I have our anodizing setup. We have our power supply unit, and we have our cathode here, which is also titanium, attached to the negative terminal of the power supply unit. And we have our electrolyte solution, which is citric acid dissolved in distilled water. We want to turn on our PSU, turn it down, not to 77 volts. We'll start off at like 40, 41. So I have our workpiece attached to this positive terminal acting as a cathode. When I submerge it, you can see the amperage goes up on the PSU, and we have a color change very quickly. And you can see the cathode is producing hydrogen gas, which is bubbling out. So now I'm going to turn up the voltage. Let me just put it back in this water for now. So I'm going to turn the voltage up to 86 volts. And I'm going to try and show you guys a gradient effect here. So I'm going to dip it in and pull it out. You see that color change? It's transitioned from a blue to a gold to a pinkish purple color. Hope you guys can see the color well. I know the lighting isn't ideal. So I'm going to put it back in the water. And I'm going to increase this to about 100 volts. Let me see if changing the angle on this will help with the view of the color. That might be a bit better. So we have our purple workpiece. We're going to submerge it. Almost a turquoise now. I'm going to turn it up a little bit more. To about 110. You should see it go green. There we go. So yeah, there we have it. This is the experimental portion, and I'm going to go on and try to explain the mechanisms behind this, why we get this color change in the titanium metal. All right, so I'm going to explain what we saw in that experiment. First of all, the first step was etching the titanium. And what that means is, so if you have a surface of titanium, like let's just say it goes down an undetermined depth. On exposure to atmospheric oxygen, this titanium will form what's called an oxide passivation layer. And what that means is over time, it'll build up a layer of oxide, of titanium dioxide on the surface of the titanium, which protects the metal from further oxidation. The oxidation doesn't dig into the titanium metal, like if you see rust digging deep into a piece of steel, for example. It forms a protective layer over the surface of the metal itself and prevents further oxidation. And this is why titanium is such a corrosion resistant metal, because it forms this passivation layer that prevents it from easily being degraded through oxidation. So in the first step, which is called etching, we used hydrofluoric acid, or HF, to strip away this oxide layer here. And when we did that, we exposed the bare titanium. And after doing so, we submerged it in water until we were ready to perform the actual electrolysis, because that prevents it from starting to grow a new oxide layer. So to anodize titanium, you need to first get rid of that natural passivation layer. And then next what we did is we essentially grew another oxide layer, but an oxide layer that was controlled in how thick it is, essentially. And we did so using electrolysis. So in this illustration of an electrolytic cell, we have our power supply unit, PSU, down here, and it has two electrodes that are submerged in this electrolyte solution. One of them corresponds to the positive, which is called the anode, and the other one is connected to the negative, and that's called the cathode. Now, the reason that this is called titanium anodization is because the titanium workpiece that we're trying to color to form that new oxide layer on is the cathode in this setup. So this would be the piece that turned different colors. In this electrolyte solution here, this is water with citric acid dissolved in it. And that gives the water the property of being able to conduct a current. Not very well, but it can conduct a current nonetheless. And that's essentially what electrolyte solution is, a solution that can conduct a current. Now, when you pass electricity through an electrolyte solution with water, you catalyze a reaction where the water molecules are split. So you have two water molecules that are then split into two diatomic hydrogen molecules and then a diatomic oxygen molecule. Now, hydrogen is positively charged. It consists of only a proton. So the electrodes attract the corresponding opposite charge. So the hydrogen migrates to the cathode, and then the oxygen migrates to the anode. And when the oxygen migrates to the anode, if the anode consists of an oxidizable material, it will oxidize that. And the hydrogen migrates to the cathode and it disperses as hydrogen gas. It bubbles off. So with the oxygen oxidizing our workpiece, our anode, it builds a layer of oxide. And the thickness of that layer is determined by the voltage that we apply, and the speed at which it builds is determined by the amperage. And there's a certain range of voltage which produces different corresponding colors. I forget exactly what the range is. I think it's like 20 to like 110 volts. So that explains what the experiment was. But why does the metal change color? That's kind of the big question, right? It looks kind of magical. When I first saw it, it was really, really cool to me how you could dip a piece of metal in some water and it would change colors. So that's going to require a bit more explanation, and bear with me here because I'm going to try and explain this in as comprehensible a way as possible, but it's a bit of an esoteric concept to explain. So I'm going to try and start with the fundamentals, the prerequisite information, and build from there. So just to start off, what is color? To answer that question, we kind of have to say, you know, what is light? If you have a source of light, it emits photons. And photons are an elementary particle that are what light consists of. They display both the characteristics of a particle and a wave, which is called wave-particle duality. And that's kind of in the realm of quantum physics, and I'm not really going to be touching that here. But for what we're discussing, we're mostly going to be referring to light as waves here, or rather, we're going to be focusing on their characteristics as waves, because that's kind of what this all pertains to. So when you have a light source, it's emitting this radiation in the form of photons. So a light source generally has many different frequencies of wavelength. You know, some are shorter frequencies, and some are longer. And so light is generally, or natural light is generally a mix of lots of different wavelengths of light. So when this light reflects off of an object, some types of waves are absorbed into the object, and the energy is converted into heat, and some are reflected. And when you have a reflected light beam, the wavelength of the light determines which are absorbed and which are reflected. So the reflected beams can then be perceived by the cones in the eye as a color. I feel like we kind of had to go over that, you know, concept. Now, what exactly is a light wave? Or rather, let's just say, what is a wave? What are the characteristics of a wave? So I'm going to draw two axes, and I'm going to draw just a basic sine wave, a sinusoidal wave. So for the purpose of this explanation, just assume that these are uniform, that the height between these and the distance between them are all uniform. This wave has several characteristics. You have the wavelength and the amplitude, which are the two ones that we're going to be focusing on. Let's start with wavelength, which is what generally determines color. So wavelength is determined by the distance of corresponding points in the same phase of a wave. So what that means is if you have 2 points, like let's say here and here, or you could also say here and here, or here and here, the distance between these points is all at the same value, and that is the wavelength represented by the lambda. So these are all the same distance, and this is wavelength or frequency. Another characteristic of waves is the amplitude. Now, the amplitude of a wave is the so-called height of the wave, essentially. I mean, from this point down to here, that's one kind of amplitude, or you can measure just half of that. I'll just label that as A, as amplitude. So generally, the wavelength will determine the color of the light, and the amplitude will determine the intensity of the light. And perceived color is determined by several factors in light to surface interactions, and that includes absorption, reflection, interference, and emission spectra, but we're just going to be focusing on reflection and interference here. So now that we have that out of the way, we briefly explain what color is and what a wave is, a wave of light. Now we're going to talk about thin film interference. Now, I'm going to refer to it as TFI for ease of explanation. TFI, thin film interference. TFI is the phenomenon responsible for the change of color in the titanium. So thin film interference, as the name suggests, is a phenomenon where color or perceived color is changed because of a thin film on a surface. It's present in several natural occurring phenomenons like the shimmering iridescence of a butterfly's wings, or the rainbowy color of soap bubbles and the rainbowy color of oil on water. It's also present in the tempering of steel, the changes in the color of steel, and in anodizing titanium. It's the product of a thin, very thin, nano to micrometer scale film on the surface of an object. And that film causes the change in perceived color, and this is how it does so. Let's say we have a surface that is not permeable to light, like titanium, for example. And then we have a very thin film on top of that surface that is permeable to light, like, for example, titanium dioxide. So if you have a source of light, the so-called incident light wave will come in, and once it reaches this top layer, even though it is permeable to light, a portion of that light will still reflect off of it. Now another portion will transmit through this first layer, or this first surface, and it will bend and then be transmitted back through after reflecting off of the second surface. So I'm going to label this surface, this initial surface, as surface A, and the second one as surface B. I don't know if you can really see this. I use pink here, but I'll just go over it in black. And I'm going to label these two reflected waves as R1 and R2. Now, when the light that is transmitted through the first surface enters this material, it bends due to the refractive index of this material. The refractive index essentially is just the ability for a material to bend light and the degree of which it does so. So it changes the angle. It changes the angle when it enters to a sharper angle, and then it reflects off of this surface, and then it comes out, and then once again the angle changes. So what you have as a result of that is these two parallel reflected beams or waves. You have to imagine this is on a very, very small scale, so these are very close together. And when you have two waves of light, or two waves in general interacting, they will interfere with each other and produce a combined wave with either less or more intensity depending on how they interfere. So there's two ways that they can interfere. There's constructively and destructively. So with constructive interference, it occurs when you have two waves that are in phase, that their phase points are aligned. So for example, so this is poorly drawn, but you get the idea. So they're in phase, their wavelengths match up, more or less. Now, what that results in is the combined wave outputted as a result of the mingling of these two waves, the interference, is that it's amplified. And what that means is the wavelength itself doesn't change. Assume these two are the same wavelength, right? So this value right here, the wavelength, is the same as the second wavelengths, or the second wave's wavelength. But what changes is the amplitude of the corresponding combined waves. So if we have this measurement of the half amplitude and we label it as A1, then in this bottom one, A1 would be less than A2, while the wavelength lambda 1 will be equal to lambda 2. So interference in general only affects the amplitude of the combined output beam. It doesn't affect the wavelength. So we're still getting the same wavelength, but with different intensity. And like I said, light sources are combinations of many waves of different wavelengths. So in reality, this is the microcosmic scale of one wave hitting the material and reflecting off, but there's going to be many hitting it. So destructive interference is the opposite of constructive, as you might have guessed. It is when you have two waves interfere with each other, and these waves are out of phase. You can see that their phase points are not aligned. So what happens here is the resultant combined wave is attenuated. It has reduced amplitude. Like I said earlier, the wavelength itself doesn't change, but the intensity does. So you have lowered intensity when these waves interact destructively. So depending on the refractive index of this material and the depth of this material, you'll have the phase of light of a certain wavelength coming out at a different point. So for example, if you had 400 nanometer light coming in here, it's going to come in at a certain point in its phase, and then when it comes out, it's going to be at a different point. And whether that aligns with the phase of the original reflected light determines whether it's intensified or attenuated, dampened. And if you had light that was 500 nanometers, it's going to have a different interaction. It might also it might be the same result. It could be constructive or destructive, both the same as the 400, but it depends on how that wave of light interacts with this material, and then at what point the wave phase is at when it reflects back out, and then how they interact with each other. So if you had like a dirty light source emitting different wavelengths of light, this thin film is gonna increase the selectivity of waves that are reflected, or rather waves of certain wavelengths that are reflected. So it might reflect more wavelengths that correspond to the color green, or it might reflect less of ones that correspond to the color red, or whatever, And what that does is it changes the perceived color of the material. Now, as you can see, this resembles our example earlier of the titanium metal with titanium dioxide coating. And this is exactly how that changes the color of the metal. You have this thin coating of dioxide that acts as a thin film, and that thin film causes the interference of these reflected light waves, and then thus changes the perceived color of the material. So this kind of explains the anodizing titanium. But what about soap bubbles and oil and water? Why are they rainbowy? Now it's the same phenomenon, but instead of having a non-permeable material as B, as the secondary surface. Let's say that this is the film of a soap bubble here, and down here below it is air, and above it is air. When we have an incident beam coming in, an incident wave of light, it's going to come in, hit the initial surface, and then reflect. And then we're also going to see the same as here. We're going to see diffraction, changing the angle of trajectory, and then we're going to see transmission back out. And it's the same principle, really. I mean, these these two waves interfere with each other and cause the perceived change in color. With soap bubbles in particular, it may have that rainbow effect because the thickness of this film probably deviates due to like atmospheric pressure and wind and whatever. It fluctuates, so it can cause the changing color effect. I forgot to mention also some light then is also transmitted through at the original angle of trajectory. Some hits the surface, reflects, some passes through and then reflects, and then some just goes through. And that's really the same concept with the water, the oil and water. Just like if this was oil film on water and down here was water, it would be the same thing. So yeah, that's thin film interference. This is the second time I've recorded this because the first time I feel like I didn't really explain it very well. And I hope this explanation did it justice because it's a really interesting phenomenon. And it's easy to get lost in the weeds with all the physics fuckery and shit that goes on with it. But I hope this was somewhat intuitive and not too esoteric and that this is understandable. Long story short, the thin film, it kind of acts as a filter. It increases the selectivity of certain wavelengths of light that are reflected out, and that causes the change in the perceived color.